Here's today's scenario. You wake up in Athens circa 400 BC, and you hear this buzz around town about this new game or challenge thing. A friend of yours hands you a pair of needles, a straight edge, and explains that you have to make these different shapes. You're supposed to make a perfect triangle, hexagon, square, and the real difficult one is a pentagon. And if you can make the pentagon, then you get into this secret club where you do a bunch of challenges and games like these. They also give you a hint that everything starts with a circle and that messing around is totally okay. And then they set you off and tell you to give it a go. So yeah, try it out. Jumping forward 2,000 years, our buddy René Descartes took a break from thinking and therefore being, and now we have the Cartesian plane. It was invented to help visualize functions. You see, functions are machines that do consistent operations. In high school, I learned functions as things with one input and one output, but it's more like in programming where they can have 0 or more inputs. An example of a 2-input function is the Pythagorean theorem, which makes these well-balanced cones. Jumping back, a 0-input function just always returns the same thing. With one input, you can have a line, and you can vary the slope of it with a variable. Add them together and you get the standard line function, y equals mx plus b. The plus b basically adds its amount to every single point. Another way to think about it is it's shifting the original graph up by that amount. The standard line is a slope and a y-intercept, but it's also positional form at x equals 0. There are more ways to describe the same line, or the same relationship between x and y. You can define it using 2 points, a point and an angle, something else. The way that you switch between the different forms is using what I call the rules of sameness. 1. Conservation of equality, or the both sides rule. Applying any operation to two equal things will have the outputs be equal. Number 2. The law of equivalent exchange. You can swap out equal things at any time. Using those rules, you can switch between the different line forms and take advantage of their strengths. It's kind of like transformers. You can even make up your own, call it a rad line, after rad. Maybe it's related to linear algebra, I don't know. The same form conversion stuff applies to parabolas and circles. But with parabolas, there's a one-way operation, or an asymmetric operation. Like how it's easy to scramble a jigsaw puzzle and boring to put it together. The difficult operation is moving from the standard parabola to factored form, so most people just memorize this mess and then move on. Back to line functions. In the standard line function, you can see where the lines intersect using algebra. It's basically asking where they have the same y value. And if the y values are the same, then you can use the law of equivalent exchange to swap the y's, and then you can solve for x. And then you can take that x and feed it back into the line function to get the full position. If you try to do that with circles, it's a little bit weird. You see, most things in math can be thought of as relationships or operations. Lines and parabolas are functions on the input x, and we graph the output as y to visualize the relationship. But the circle is different, because it's a relationship, but not a function, at least not in the same way. So I searched up how to do this on YouTube, and it worked, but it confused me. So here's how you do it. You start by changing them to this form, then using the both sides rule to move everything to one side, so they're both equal to 0. But here's the thing, they're both equal to 0, so you can use the law of equivalent exchange to make them equal to each other. This is effectively asking where these circles are the same. Then you use the both sides rule to move everything to one side, and then you're just subtracting like terms. And what you end up with is this line. The keen observers out there will notice that the squared terms always cancel each other out. So you didn't have to start with circles. You could have started with lines, parabolas, or music theory YouTuber parabolas. So I figured all of them were related and tried graphing them. So I noticed that the circle is tangent to the zeros of the parabolas, even the imaginary ones, and the line is tangent to the parabolas. So this form connects lines, parabolas, and circles really meaningfully, and it's equal to 0, so I called it zero-suit form, after Samus. So I messed around and turned the new line into a circle, and did that recursively and got this. To find the points where the two circles intersect, we can rearrange the line equation so we can sub in either the x or the y value into the circle equation using the law of equivalent exchange. And that gives us a parabola. And finding the exact 2 points where the circles overlap involves solving a quadratic. So I went to this 3 blue 1 brown video about solving the quadratic the better way. Solving a quadratic means finding the zeros or the roots. In that video, he talks about how multiplying things together is tied to subtracting squares. So for every product, for every result of multiplying two numbers, there's a difference of squares related to it. So that could be a way to find the primes. Not necessarily a good way, but it's a way. The way it works is that you take some mean or midpoint and then add or subtract some distance and multiply those together and it makes a rectangle. And that rectangle can be rearranged to be a big square with a smaller square taken out of it. Basically, the difference of squares can be rearranged into a rectangle and vice versa. And rectangles are a form of multiplication. So, multiplication is also a form of subtracting squares, which is wild. Variations on this factor thing, like adding squares, doesn't have the same quirk. In the video, he moves on to talk about the simpler quadratic equation, which uses the zero-suit form of the parabola, but with the y scaling variable set to 0, which is needed for the algebra, but doesn't help us see it. So I added it back in and set it to 1 in this thing I programmed. The orange area is the square with one side connecting the two roots. With no added c value, 0 is always one of the roots. The pink rectangle has a width of 1 and has the same area as the square, so it shows how it's connected to the original parabola. And with the variable c, you can add and subtract area, but it gets kind of funky because the square is connecting the roots. But parabolas are all about having squares from the middle to one side, and the square there goes all the way across. So making a square with half the distance would make more sense. The variable c adds area, not length, so it shifts everything vertically. So the midline stays in the same spot, so we can ignore c for a minute. If we ignore c, we can find the two pseudo-roots. Like I mentioned before, one of them will always be 0, and then the other one will be the variable a. So the midline is just half of a, and half of a is also the current pseudo-distance from the midline. When we have those, we can add the positive or negative area of c back in, and that gives us the new area. If we take the square root of that, it gives us our new distance, the real distance from the midline. And that's how you solve a quadratic visually. I think this thing's pretty neat. If you want to check this thing out, there's a link below. Now that we solved one of the parabolas, we can plug those numbers back into the line function and get the full positions of where the circles intersect. And that's how you teach a computer how to use a compass and a straight edge. Now, you might be wondering, why? Like, when are we going to use this? Lines can model things in the real world, such as depth and pressure. They're also useful in statistics, where all sorts of weird curves can be unsquished into lines. And programmers will definitely be using functions. Parabolas show up everywhere that there's a square term. So equals mc squared, there's probably a parabola in there. Although it might involve parallel universes where there's different speeds of light. Or if you want to model acceleration due to gravity for your barbarian that jumps halfway to space, then you can do that. And if you know a little bit of calculus, then you know they go at least Mach 14 at launch. And polynomials like parabolas are a good entry into calculus, because there's a shortcut that makes moving up and down levels fairly easy once you understand it. And calculus is a hammer you can hit anything with. And it does a lot of work for little effort, at least once you understand it. It's one of the things I'm learning about in this book I'm reading called Burn Math Class. Anyways, back to that challenge. If you were able to make a perfect pentagon by making a regular overhand knot with a strip of paper or cloth, then you achieved the goal of not only making a perfect pentagon, but also, more importantly, upsetting the people in charge. The people in charge had to make a new rule saying that capital M math uses only a compass and a straight edge, which is hilarious. Stay mischievous.